So good afternoon. Welcome to the sixth week of the facilitation for physics 313 class. Um, we are gradually getting close to the end of the class. So today we shall be looking at complex integral, which is was the lecture scheduled for the sixth week. Um, like I told you last week, somebody sent some questions to me which I look at, and according to what the person said in the class, that some of the questions are not part of the lecture. But when I saw the question he sent to me, I disagree with the person. The only thing is that questions in that past questions are not the same questions we treated in the class, but the same idea that we used to treat the question in the class, what was you are expected to use to solve the problem. They are just the same thing. The same principles, the same technology, terminologies, and the same approach are what I expected that you should use to solve the problem. So telling me that they are not the same thing. You are not expected to see 2 plus 2x plus 3y in the class, and you're expecting 2 plus 2x plus 2y again in the exam. No, 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 no. You will not see such things. You'll be expected to use the same approach used to solve the problem in the class to also solve similar problem. That is what I saw in the question. So just take your time to understand what we have discussed over. I believe you should be able to answer most of the questions I saw there. They are not something difficult. So, but before I proceed in depth into today's discussion, so there was a question last week that has to do with some of the uh, assignments in this uh, for example, question 4. Now, like I promised that I will solve and send across to students, but I was busy, I couldn't do that. But in the meantime, I can quickly give you a guide on what you are expected to do in that case. So if you look at, let me just show you one Google uh, example on how those problems can be solved. Now, if you look at this now, this is a Wikipedia information. Look at this. This is a coach. Look at this expression. This is coach. And you can write this as coach Z, like we have in the problem. Just a moment, I'm coming. Like we have in this problem. This is cos. So you can write this cos X, cos Z as cos into bracket A plus IB. Then you now use strict function. You use strict function to express it. For example, now if you look at this is cos A plus IB, it can be cos A plus BI, which is Z now. It will now be cos A cos BI, like this. You expect like this is what you are expected to do for each of these functions. You have cos, sine, and coch and sine. This is what you are expected to do just to express it in that form. Then you can expand. I think that is clear now. So any question on that? If none, then let's proceed to what we are expected to discuss today. So today we shall discuss complex integral, and if time permits us, we also go to start something about residual theorem. So in complex integral, it is just a way of solving some complex functions. So we said let f of t equals u of t plus I v t, where u of t and v of t are real value functions of the real variable t for a less than t, less than or equals to t, and t less than or equals to b. Then this expression now, we can write it in this form. Integral from a to b, that is the boundary now. You know, there's something we call definite integral in integrations. So which means when you tell you that this is a definite integral, that is, it has a boundary from the lowest to the highest. If these a and b are not there, we refer to integral of this form as indefinite integral. So in this case, these are definite integral, and if you are integrating a definite integer, at the end of the day, you have to substitute what the value of a and b are inside the expression that you are going to obtain. So f of t, now if you said f of t is equals to this, then if you replace f of this in this expression with the whole of this, now you have u of t plus ivt, then the t. So meaning that if you allow this definite integer sign to go over them, you can have them in separate. This is one and this is second one. So this one is the real part and this one is the imaginary part. So that is the first approach called A. We can also evaluate integral of this type by using derivative, antiderivative of u of t and b of t. So in that case, u prime of t is equals to ut and v prime of t is equals to this. So we can write this thing as like this, and that will now be u of b minus u of a plus I vb minus v of a. So now let's see an example. So the first example here is that show that integral from 0 to 1, which is from a to b. Now our a is 0 and our b is 1, of t minus 1 to the power of 3 dt is equals to this. You are asked to prove that if you integrate this using this approach, your result should be minus 5 over 4. So what are we expected to do? The first thing you are expected to do is to find a way to expand this term, t minus 1 to the power of 3. So you can see that f of t is this. Then when they expand it, they now write it in a form of the real term and the imaginary term, just like this. Just like this function now. So you now have it. So t cube minus 3t, which is u of t, and vt, which is equal to minus 3t plus 1, is now our v of t. So now, since we know that if you have function of this nature and you are able to write it in this format, then you cannot perform integration per term like this. So the first thing here is u of t, which is this. Then you integrate it, substitute the value of the boundary 0 to 1 on it, you have this. Do the same thing for this now. This gives you 0. So automatically, by the time you are writing the expression, that is d of this can be written in this form, which is now the result of this, y is minus 5 over 4 plus 0I, and the answer is minus 5 over 4. That shows that when you integrate this expression, you get this, and that is what you have just established here. Any question on that? Now let's look at the second question. Here you have to be very careful and be attentive. Try to understand one or two things, because a lot of information are hiding in this solution. So I will try to explain to you a step after the other. Now they say show that integral from 0 to pi over 2 of exponential t plus it dt is equals to this expression. Now if you look at this expression now, this one, you can rewrite this expression in such a way that the positive sign will be taken away. And if you want to do that, you have something like this. Integral of this is equals to this now, because they have the same base, and this multiplication you can add the power. That is what give you this. This is just the law of logarithm and also law of indices in mathematics. So now if you now have this now, so this one having it now, we know that exponential it can be written in this form. We have discussed this in the first part of the class. You can write it in this format. So now if you now look at this now, you know we have established a different equation now. We can open the bracket by multiplying through by e to t for each of the term. Then you now have this, then this. So if you look at this now, it's just like an integration by parts expression. So where this first term can be written as our u, and this second term can be written as our dv. So from that, we can solve this and this separately and later combine them. So if you are trying to evaluate them now, looking at the first one, so this now, if you apply integration by part expression, which says that if you have integral of u dv, which is equals to uv minus integral of v du. So if you look at this now, what you have here is uv. And how did they get their u? This first term is the u, and this second term is the v. So by integrating this now to get your v, integral of cos t will give you sin t, and that is why you have this and this. And this is u, this is v. But they have boundary from 0 to pi over 2. So this part now is just v dv. V du rather. So since our u is equals to e to power of t. If you now have the u, the t now, it's going to give you exponential t. That is what gave back to this term. And we know this already. It's our v du, which is this term. So now, by the time you open this bracket, integrate this, and substitute, you have this. Breaking it down further, you're just trying to solve one or two things together. By the time you do it up to this point, you're just expressing substitution, deducting, and all these things. Gradually, you arrive at this point, which later give us that the whole of this expression is equals to this. Any question before I proceed further? Any question? John,
Sir, good evening, sir.
good evening. How are you? Do you have question? You are the only person in class today.
Yes, sir.
Okay.
No question for now.
Okay, good. So now we can also use another format in solving most of these things. The complex integrals have properties that are similar to those of real integrals. We now trace through several commonalities. So let us mean that f of t is this, and we write g of t also to be this. Be continuous on a less than or equals to t and t less than or equals to b. So by the time you use a definition of a, that is the first definition we have here, this one here, because we are going to combine all the definition. We use the first definition of a, we can easily show that the integral of their sum, show that the integral of their sum is the sum of their integrals, that is f of t plus gt. Now you just integrating f of t and g of t, then you add them together. That is what it's trying to say. But now at different boundary now. So if you now look at it, if you divide the interval between this into two, that is you move from a to c and now from c to b, you know, you have introduced a c, an intermediary. So the integration of f of t over this sub interval by using a, so we can have this now. We integrate from a to c of f of t, then from c to b. Since we know that the complete procedure is to integrate from a to b, so you can split them to integrate between a and b and find a point of c. At the end of the day, you are still going to have the same result. So similarly, if alpha plus I beta denote a complex constant, then this integration of a to b of c plus I d f of t dt, you know, this is a different expression now. Because the whole of this now is a constant, you can take it out of the integral. So you have it like this, then you have this, which can be easy to integrate. So if the limit of integration are reversed, that is, you are looking at the negative part of it now, it's still the same. That integral of this will give you minus integral of b to a f of t dt. What has happened here is that initially we move from a to b. Let's assume that we are moving from b to a now. It's just like if you are multiplying by a negative sign. That is what this expression implies. So we now have the integral of the product of this becomes this. Then by the time you multiply and open the bracket, you have series of expression which you can later break down and collect the ones that has I and those that doesn't have I, so that you can now have the real and the imaginary part. So now let's look at some examples now. Okay, let us verify property E, that is, they are referring to this property, this expression. We start by writing, we have this, then you open a, we know that f of t is this. So if you open the bracket, now you have cu of this, just like algebra of a thing. So you expand them. By the time you expand, then you introduce the integral per each term. So it's just like taking your pencil and start breaking down. At the end of the day, you arrive at this point. So which eventually resulted to integral of a to b of this is equals to this of this. So it is worthwhile to point out the similarity between equation B and its counterpart in calculus. Suppose that u and v are differentiable on a and b, and ft is equals to ut plus ivt. If you look at this now, it's not capital T, it's not small t now, it's not small f rather. So if you take derivative f prime now, it will be this. So which is ut plus ivt is equals to f of t. So equation B takes on the familiar form of this. So f of b minus f of a. Let's look at examples here now. So using equation h to show that the whole of this is equals to, you know, you have solved this earlier on. So you still want to solve the same problem using another approach now, using this approach, this one, to see if you are going to get the same result. So what you are going to do here is that you take the function and take the derivative of the function. So that's what happened here. We seek a function f with property that f prime t is equal to this. So we denote that f of t is equal to that. They take the derivative of this function and it give us this, satisfy this requirement, so that once you take derivative, you have this. Then you substitute from 0 to pi. Then you expand it, and that gives you this expression, which is what we obtain when we use the property A. So now, any question on that? So now, you are expected to solve this problem. This one, use equation H to evaluate this problem now. You are expected to use the same approach. This one that we use here, this H here, this one. The first thing you do is that you take the function and take the derivative. And once you take the derivative, you just substitute the limit into the derivative, and that gives you the result. That's what you are trying to do here. This one is more or less like the one that has t minus 3. You are just to expand this to the power of 5 and later group them to the real and the imaginary parts. Is that taken? John?
Yes, sir.
Okay. So any question for me? If there is no question, so let's briefly discuss some things about residual theorem, because I hope to complete this class next week. So, and there are a lot of things to discuss under this. So let's look at the basic things today before next week, so that we can be able to cover it next week. So we said the residue theorem, sometimes called Cauchy residue theorem, is in complex analysis is a powerful tool to evaluate line integrals of analytical function over closed curve, and can be often be used to compute real integrals as well. It generalizes the Cauchy integral theorem and Cauchy integral formula from a geometrical perspective. It's a special case of a generalized Stokes theorem. So the basic thing behind this is that we use it to solve problems that has to do with curve and shapes. So now let's look at some of the theorem now. You say, suppose U is a simply connected open subset of a complex plane, and A1 to An are finitely many points on U, and F is a function which define an holomorphic on this. So you have integral. This is if you see this type of sign, is a closed integral because of this cycle on the integral sign. So the integral on the close of f of z dz is equals to this. This is an expression. We have I of this and residue of this. So if gamma is a positively oriented Jordan curve, so I of this equals to 1, and so f of this is equals to this, just only the residual. So the residual function. So these are stories, but we need an expression here. Okay. Let's go down. Now let's look at an example. Then we see how this thing is being done. Say the integral of negative infinity to positive infinity of exponential itx divided by x squared plus 1 the x. So we want to integrate this now, and we want to use these procedures to solve the problem. So the question now is that if you look at it now, look at the expression very well. You see that the only variable here is z. Now, no, it's x rather. So trying to use that function in terms of the residual theorem, you have to find a way to change your x to z. And that is what happened here. Now, integral of this c means a close of f of z is z. In terms of that function now, where you see x, you put z. This is, you know, you have x here now. So you replace x with z. So which give us this. So now, since I is here, I exponential itz is an entire function having no singularity at any point in the complex plane. This function has singularity only where the denominator, that is this, is equals to 0. So since z squared plus 1 is equals to z plus I and z minus I. Do you know the reason why they have this?
Yes, and it to complex function.
Okay, good. So what happened only when z is equal to I or z is equal to minus I? Only one of those points is in the region bounded by this contour, because f of z is this. So now they try to simplify this. Exponential it z squared plus 1, which is this now. Is what they have done here is just trying to expand this z squared plus 1, which is this now. If you expand this now, which is what they have here, they replace the whole of this with this, so it should now be this over this. So in that case, you can find a way to, it's just an algebra, so that to rewrite this expression in this format using this principle. So let me just give you an hint there. What happened here is that you know something we call partial fraction. John,
Yes, sir. Yes, sir.
you know what they call partial fraction.
Yes, sir.
So if you bring that idea of partial fraction into this place now, you will see clearly how to write the whole of this with this term in this format. That's what they've done here. You can try that. You know, when you have a function in partial fraction, you can write that function as a over something plus b over something, depending on the power of the denominator. Are you getting me now? So that was what was used here to expand this expression. You can check it. So now the residue of f of z now at z is equal to I now, which is the positive term now. If you substitute z now to equals to I now, in this case, the whole of this goes to 0. So if z is equal to I now, this will give you 2I. Then I times I, that will be I squared. And if you now have I squared is now negative. Then the negative will cancel this. And that is why you have this. Are we together? So the residue now,
Yes, sir.
the residue now of z is equal to I of z is now equals to this, because they've replaced I with all these functions, and that gives them this expression. So now, according to the residue theorem, then we know that this is the theorem, which is this. So where you have the whole of this now is equals to this. So you just replace the whole of this with this, and you expand, and that gives you pi exponential minus t. So the contour C may be split into a straight part and a curved arc, so that the straight will be this and the arc will be this, which is equals to this. You know, the best way to understand this is to try to solve the problem and try to bring in the idea of some of the theorems in mathematics, that is most of the algebra experiences, like the partial fraction that I just told you now, and also the complex number approach that we discussed in the earlier part of the class. So with that, we get this result. Any question? John, any question?
For now, no.
Okay, fine. If there's no question, I think it's good for us to stop here, because I can see that you are the only person in class, so that others also can follow us when we are discussing in detail of this residual theorem next week. Do you agree with me?
Yes, sir.
Okay, so thank you very much for coming. So I have to stop the class.